Hi everyone. To kick off this week, we're going to have a look at linear modeling, and that will finish off our um, part on linear functions in general. Now, I have to say that understanding how to take a worded question or a real world problem and model it as a function so that you can use it is quite a complex skill in many ways. It's partly a literacy skill because you have to understand the question, partly a mathematical skill as you analyze or synthesize the question and turn it into a function you can use. So there's a lot going on. The good news is that linear modeling is pretty straightforward, and you're probably going to think I'm over egging it this week by going through all of this detail when you can probably just look at a problem and know what to do, kind of thing. If you're one of those people, please do note that what I'm looking at here is designed to try and get you to step back from the idea that it's linear and just have a look at modeling in general and have a look at a general approach to a real world problem and how we might go modeling it. If you're the kind of person who's never really got how to go from a word problem to a mathematical modeling of that problem, then even linear ones, then this is the right video for you, right? So here we go. What we want to do here is we're going to go from a real world scenario. I always put real world in quote marks because in maths it's kind of almost always made up. But the idea that you're taking real world data and doing something to it is absolutely super critical. Quite frequently, what happens is that you've run an experiment or done a survey or something like that, and you've got a whole set of data points that you've got from running it, and you plot those dot points and you find that you've got some sort of relationship between one variable and the other. And that relationship might be linear, it might be exponential, it might be trigonometric. You never know until you've plotted the data and had a look at it. But from there, you're supposed to make a model up and so on. Alternatively, you've got a scenario in mind and you then need to go about turning it into a function so you can use it. So you've got some sort of real world context, you turn it into a function. Once you've got a function, you can graph it, knowing that it's just an approximation usually of the real world. And in maths, that's why I put it in quotes, because in maths, that approximation is kind of given to you as very, very specific values and numbers. But anyway, once you've got the function, you can then graph that approximation. And either between the function or the graph or both, you can then use it to do a bunch of things. You can use it to work out specific values that you didn't actually plot for yourself or find out for yourself, or maybe you can predict what's happening in the future. Knowing that the more into the future you go, the less likely it's going to really capture a real world kind of model. But in a linear model, it's not that difficult to sort of determine what's going on, really. So again, just keep it in mind that I'm trying to teach just general skills of modeling to start with. So I've got these 5 points here, really. I'll go through them one by one. It would not hurt you, though, to pause the video right here and write these 5 steps down, really. Well, not really steps, but 5 points. So pause the video and then I'll come back and explain them. Okay, hopefully you did do that. You paused it, you've written it down. So the first thing you need to do is decide what kind of model it is. Now, obviously, in a linear modeling section, it's going to be a linear model, but we'll have a look at this in more detail in a second, and we'll start looking at what kinds of things to look out for in a worded problem or a real-world problem that seems to suggest that it's going to be linear. The second thing is, what critical information do I need? Actually, you know what? I might just zoom out. Don't worry about the example on slide 3. And do note that there is a 6 point here. I forgot to mention that earlier. So again, you might want to pause and write that 6 point down as well. Okay, assuming you've done that. So how about I just sort of give you a bit of an idea about what we're looking for in a linear model. So what kind of model is it? So for a linear model, you're looking for, the thing about a linear function is that it's directly proportional and it's constant. So of the two variables, usually x, which is the independent, and y, which is the dependent, we're looking for some sort of constant proportion between those two variables. So that's the first thing, but that's a bit hard to sort of quantify really. So constant proportion, as one thing changes, the other thing changes accordingly at a similar rate. So that's the kind of phrasing you're looking for. You're looking for a rate or something like that. Something which gives you the idea that it's something is changing constantly at the same rate. Could be something like a speed, could be lots of different things. Number two, what critical information do I need? Okay, now we're getting into regular old territory. For a linear function, what do we need? We need a gradient, and we need a y-intercept. They're the two key things, right? So what does it look like in a question? Gradient is almost always some kind of rate. Okay, so that's what you're looking for, something which gives you a something per something kind of idea. It might be that you're not given the rate, but you're given two pieces of information that allows you to work out a rate. So it's not always exactly right. Y-intercept, what you're looking for is like an initial or starting value. It might be t equals 0, or it might be started at, or something like that. So that's an initial or starting value. Again, you don't always get it handed to you on a platter. It may be that you're given enough information so that you can determine the critical information. So that's number three, really. What do I have that fits or allows me to work out the critical information? That's the bits in red. I should have put it here, really. That kind of thing is what you're looking for. Number four, make the function. So we know the function is y equals mx plus c. So you need to put stuff in to make that work. Number five, sketch or graph the function. And just keep track of things like, is it going to be positive or negative or flat? And the other thing you need to point out is also what possible values as well. What do I mean by that? Legit. I'll put that there. What possible values are legit? Okay, what I mean by that particular point is that that you've got to be sort of a little bit mindful that if you're doing a real world problem, not all values are going to be ones that you can use. So, for example, if I was doing a height versus distance away or something like that, it may be that talking about a negative height does not make sense in the context of the problem, or talking about a negative distance does not make sense, or talking about negative time does not make sense. Don't be quick to assume that it will never make sense. You should think carefully about the question, think carefully about the context, and then when you're drawing your graph, draw it accordingly. Okay, I'll leave that there. I'd like to circle these bits. It's usually the negative bits that require questioning. So yeah, I'll leave that there, and we might just go straight into an example. Now, what I've said in number 6 there, use the function to answer questions or do a what-if analysis. I don't necessarily mean that like in the banal kind of like, what is the distance when t equals 7 kind of thing that you might be given in a textbook or even in a test, but just pulling back from exams and tests and all that kind of stuff and say, if you've got this linear model, once you have the function, you can then ask yourself questions. You can say things, okay, I've got this linear model to describe, I don't know, the cost of hiring a bike over over a certain period of time. Well, what happens if I want to take the bike out for 7 hours? What does that look like? And you can use the function or the graph in order to answer that question. Or I've got, $45. How long can I hire the bike? And you can use the linear model to answer that question. So I do mean that in a more rich sense, not just like can you answer a question from the textbook. The what if analysis is really useful too, because once you've got a y equals mx plus c, the what if analysis says, what happens if I change the parameters or the critical information? So, for example, what happens if I, instead of, if you're modeling some sort of profit for a business you're running, what happens if I instead charge them $12 per hour, I charge them $10.50 an hour? How does that affect my profits? What happens if I have a call out fee of $7 instead of a call out fee of $5? How does that change my overall profit? All that kind of stuff. So once you've got a function, your capacity to sort of diversify what you're doing, to try and come up with different answers or to game different situations is really useful. Okay, I know I'm over talking this, so I'm going to just go straight into example 2G, and I'm going to try and follow those steps as carefully as I can. So example 2G, question 7, page 64. It's a fairly simple problem. Let's go through it. And hopefully it'll sort of make more sense what we're doing here. So you can read it for yourself, pause it and read it. I'll quickly read it though, in case that's useful to you. Two towns, A and B, are 200 kilometers apart. A man leaves town A and walks at an average speed of 5 kilometers per hour towards town B. I've got average in blue there because the question in the textbook does not have the word average there, but it is really common to see it, because then you don't have to worry about questions like, surely that man is not going to be traveling at 5 kilometers per hour the whole time. He might go a bit faster when he's starting up and might go a bit slower when he's towards the end there. He's not going to keep a constant rate of 5 kilometers per hour. But if you chuck in the word average there, and then suddenly it makes sense. He may go fast, he may go slow, but overall he's going at an average of 5 kilometers per hour. So it's a constant rate. Find the distance of the man from town B at time t hours after leaving town B. So as soon as you see something like average speed of, we can see that we're talking about a constant rate. So number one, and of course, if it's a whole question on linear modeling, you don't actually have to answer this question. But that's why it's linear. It's linear because it's a constant rate. Number two, what do I need? I need to know the gradient and I need to know the y-intercept. So the next thing I'm going to do is I'm going to try and find that information out. Again, it's a literacy question. You have to keep on reading through. It would not hurt at all to read through the question multiple times until you pick out all the critical information. Sometimes it's good just to read the bit that you're looking for. Sometimes it's good to read through a few times and see whether you can pick out numbers and facts that you think might be useful later on, even if you don't know how. In this instance, it's linear. It's pretty straightforward. I'm trying to pick out the rate here. I suddenly see average speed, so I know that's important, up 5 kilometers per hour. So I'm good for that. I can write that down. Oops, that was a bit dodgy. Try that again. M equals 5. The next is actually a little bit more interesting, I suppose, in that we need to work out the y-intercept. Remember, it's the starting value. The only other fact I haven't really used at the moment is that two towns are A and B are 200 kilometers apart. So I'm going to have to ask myself, do I make the starting value 0 and B is 200 kilometers away? Or do I make the starting value 200 and then B, it will be 0 once I've reached it? In other words, am I going up? Am I going up towards 200 or am I going down to 0? And when I read the rest of the question here, find the distance of the man from town B, the distance from town B. So I'm starting at A, but he's walking towards town B at time t hours after leaving town. That should say town A, I beg your pardon. I'll just change that now. That's just me not writing that properly. So given that, I think what I'll do is, you can't go wrong too much as long as the final interpretation is appropriate. But I can see I've got 200 kilometers there, so that's fine. And I'm going to use that as my initial value. I might have used an initial value of 0. Just keep that in mind. I might have used an initial value of 0. But in this case, not having a good day today, am I? I'm going to use C is equal to 200. Okay, it might be worth doing a quick sketch off to the side here. It might be. You know, you might not have done a very good job here, but sometimes having a graphical representation does really help. So I might say, okay, well, I'm going to start at 200 kilometers away. I'm going to end at 0 here. So that's town B, that's town A. This is not meant to be a proper graph. It's meant to be just so I can try and visualize it, and I can see that it's going to go down like that, but in a linear fashion, not like I've drawn, at 5 kilometers per hour. So as soon as I draw that, I can see that I've got a downward slope. So I'm going to go back to my M, and I'm going to write -5. So although the speed is 5 kilometers per hour, I'm effectively cutting off 5 kilometers from my trip as I go along. So drawing a picture is just really handy for that kind of confirmation of what I'm doing. Number 4 is to make the function. Well, I've got the critical information. I've even drawn a little graph to help me. So I've done step 5 before step 4. So now I can write, well, I could write y and x, but I think I might use letters that are a bit more appropriate. So I might say the distance from town B is given by -5t, t for time. So I'm going to go back to my graph now. I'm going to write t and m there. -5t plus 200. I wouldn't blame you if you'd written 200 minus 5t there. So there's my function. I've already done a little brief sketch. I might, if I'd done that a real scribbly sketch, I might then go and write it up more neatly if I think that would be useful to me. Note that this area here and this area here is not filled in, the bit in red, because not valid, really, for the context. If that kind of makes sense. So that area is not valid. And in terms of what the question was asking, find the distance of the man from town B at time t hours. This is basically it, right? The distance is -5t plus 200 for a certain t. But now I can say things like, for example, how far away. So these are questions that I'm asking. I'll just do it in a different color so you can see that's different. How far away after 2 hours? Now that I've got my function, I can just go d equals -5 times 2 plus 200, which is equal to 190. It's not that mind-blowing, is it? I mean, you don't really need a function in order to do that. But again, if we can master this kind of thinking for simple problems, we can then apply the same thinking but to harder problems. We can also ask the classic sort of how long, sorry, to get to halfway, say something like that. So how long to get halfway? Well, to get halfway, we would be at 100 kilometers away, right? So I'd go 100 is equal to -5t plus 200. I can solve that. -100 is equal to -5t. So t equals 20 hours. So it will take him just under a day if he doesn't sleep to get halfway there. And that's when you start realizing that your model's a bit crazy, that I don't think he's going to be able to get there very easily by constantly walking at 5 kilometers per hour, that he's going to, either have rest stops and whatever else. And so my model's not going to really work in the real world as if it was going to ever. But you can also do things like, what if he jogged at 10 kilometers per hour? Is that more of a run? I don't know. So then you could say, let's just say it's the same thing. How long to get halfway if he jogged? Well, that'd be 100 is equal to -10 times t plus 200. -100 equals -10t. And this is amazing. T is now equal to 10 hours, half the time if he goes twice as fast. Again, not amazing stuff I'm talking about here. But if we can do it for linear, we can do it for quadratics, we can do it for exponentials, we can do it for logarithmics, we can do it for trigonometric ones. So again, getting the modeling right is more important than how difficult the problems are. Okay, I've overtalked this one, but I hope it was really useful for you to see this. I might do another example video if you need it. Just shout out if you do. Otherwise, have a go at some of the linear modeling textbook work, and yeah, we'll go from there.